All right, hi y'all. We will get started. Okay. So great. We only have 2 more weeks-ish, right? 2 more weeks of me. You have full week of class next week, or yeah, full week next week, and then only 2 days. So in terms of the final and final review, I'll do a review session next week. And then it just depends on if y'all want a review session in person or on Zoom for the final. I will do one like the night before, and then for like review session, like if you would do, okay. I might just do both of them on Zoom. Just because I think Wednesday's a reading day, so people might not come to campus anyways. And then finals on Thursday and Friday just might make it hard to have an actual room available. So I might just do this again in 2 weeks just on Zoom so that you have like a week to prepare, and then a review session the day before as well. All right, but that's a little bit away. And then you should have taken quiz 5 on Monday. I'll release the answers for that, or like you can see your choices after this, and then quiz 6 in 2 weeks. So just be on the lookout for that. Alrighty, topics for today. What are we interested in? How did we feel about the material from today? You want to go over that first? We'll just do a recap on that. All right. So what we're looking for in this next chapter is reaction rates, right? So this is how fast a reaction happens. Or it can be how fast a reactant is used up, or how fast a product is produced. So when we're looking at reaction rates, there's two ways that we can look at this. We can have a reaction that's like 2A plus B forms 3C. And in this case, we have 2 reactants and 1 product. Whenever we're looking at just the reactant or just the product, we can look at their rates specifically to one another. So how we do this is by taking the rate that the reactant is consumed and making that equal to the reactant, or to the rate of which the product is produced. So you can have the change in concentration of A over the change in time as a rate, right? Their change would be final minus initial. Your final concentration of your reactant will always be less than what you started in, right? If we look at, or if you think about just a reaction proceeding, you have to use some of those reactants in order to make products. So in order to have a final minus initial that's negative, in order to negate that, we're going to call that a negative rate change in time. Negative change in concentration over change in time. That takes your negative concentration or change in concentration and makes it positive. The other component to your rate of reaction is the coefficient in front of that reactant. So this 2 here, you want to take the reciprocal of that 2. So you would have 1/2 for this. By itself, that doesn't really mean a whole lot. But when we compare it to the rate of B, we now have change in B over the change in time, also negative, but this time the coefficient's 1, so the reciprocal is just also 1. Okay, so those rates are equal, and that's saying that for every 2 A's that are being consumed, 1 B is being consumed. And in terms of rate, the rate of B, or the rate of consumption in B, is half as fast as the rate of consumption of A. Other way around, you can say that the rate of A is twice as fast as the rate of B. So, right, if A is twice as fast, in order to make those equal, you divide it by 2. That's just for the reactants. That's just for the reactants being used up. You can do this for the products and being produced, and you could say that the production of C, which would be, right, final minus initial, your final is always going to be greater than the initial, because usually the initial is 0. You would have a change in concentration of C divided by the change in time. What would be the reciprocal for your product here for C? 1/3, right? So in the same way that we could say A is being consumed twice as fast as B, we can say that C is being produced 3 times as fast as B is being consumed. Okay, and then you can do the math for the A to C, right? You could also make a relationship there because all of those were going to be equal, right? So you could also say that this is equal to this directly. Okay, so that's one way to show rates. Any questions on that? I'll give you. So a question that you can ask is, okay, so for this question here, we have, given the reaction below, if NH3 is consumed at a rate of 5.8 times 10 to the negative 2 molarities per second, what is the rate of production of H2? Okay, so how would we go about solving this one?
Whole first term would be the A.
Yep, so this whole first term is A. So NH3 is by itself, it's our only reactant. So, right, that's like taking the place. This guy is taking the place of this guy, right? We're given a rate of 5.8. We need to make this equal to each other. So you like just pay attention to if you're being asked about a reactant or product. If you make the rate negative when you plug it into your equation, then you would get a negative rate of production of a product, which doesn't exist. So you can use that positive rate as is. So when you solve for this, you would have 1/2 change in concentration of NH3 over time equal to 1/3 change in H2 over change in time. Right, I guess this could be given to you as negative. Negative 5.8, but usually don't give rates as negatives, so. The word consumed is like giving you that negative component towards it. Okay, does everyone understand why we used NH3 and H2 this way? Okay, remember that this whole portion is the rate. So when you're looking for the rate of production of H2, you'll take 1/2 times the 5.8 equal to 1/3 times X, right? We don't know the rate of production of H2, and that whole rate of production is the change in concentration over the change in time.
It was like 4 in H3 would just be 1/4.
Yep, so
So whatever our like, the first number is, we just divide 1/whatever.
yep, it's just the reciprocal of it. So, right, in the 2a plus b goes to 3c, we took the reciprocal of 1/2. B, right, the reciprocal of 1 is 1. And then for 3, it's 1/3. So, right, if something was 1/2 a goes to 2b, right, then it would be 2 change in concentration of a over change in time. Right, you just want to make sure you flip whatever it is.
Why is the change there like not negative to that one versus like the one?
So when we say that NH3 is consumed, this word consumed is telling us that it is reactant and it has a negative change. So instead of telling you that your rate is a negative 5.8, because usually rates are not negative, they're telling you that it is consumed, which is the negative portion of it being a reactant. So you could say, or you could throw the negative in here and then put your negative 5.8 and it would cancel out. But at the end of the day, you want a positive answer, so you can just make it positive. Okay. Great questions, everyone. So I think you should get X is equal to 8.7 times 10 to the negative 2 molarity over second for your rate of production.
That's the change in H2 or just the change in time using the X value, or would there need to be more given to us?
For this question, that's about all you could answer. You could be asked, right, how much is produced in 10 seconds kind of thing, and then you would take your rate, multiply it by 10. Or you could say this much was produced over this much time, or like this much was produced, how long did it take to do that? But you would need a little bit more information in your question in order to do something like that. Right, because now you're given a rate, so now you're given units of molarity divided by seconds, so you can kind of just go from there. That's a great question. Okay, this one's not too bad. You're just looking for the wording of this one really, and making sure you have a balanced equation. On quizzes, I don't know if we give you balanced equations every time, so just make sure you're double checking for balanced equations. All right, any questions on just like initial rates? Okay. So then the next thing we look at is rate laws. Okay, so when we do a rate law, this is just utilizing your reactants. Your rate law or the rate of the reaction is only dependent on the reactants in your equation. Okay, so no products when it comes to rate laws. All right, so when we do a rate law, your rate, do we know the components of the rate law? What goes into a rate law? Your rate is going to be equal to something. K, I like that one. Right, K, lowercase k. Perfect. Yep. Yep. Perfect. So for rate laws or the rate equation, we're talking about that skeleton of an equation there, right? The rate or something, whatever how fast something is going is equal to K, little k. What do we call little k? Mm-hmm. Okay, we call that the rate constant. The concentration of A is that at the initial, middle, or end of the reaction. That's your initial concentration. That's going to be the same for A and B. And what do we call M and N? Mm-hmm. Those are going to be your order of reactant. What are the three orders we usually talk about? So we usually talk about 0, 1, 2. Other orders do exist. There are like 3/2 orders or 3 orders. But you are responsible for 0, 1, and 2. Alrighty. It is important to note that rate for your units of rate are always going to be in concentration over time. What this means is that it will most likely look like molarity over seconds. But we're talking about concentration. So this can be the little n molality, if you remember that, over hours. It can be molarity over years, right? It really just needs to be some form of concentration unit. It could be parts per million over whatever. It has to be some sort of concentration unit over some sort of time component. Most often than not, it will be molarity over seconds. Your concentrations of A and B, these are usually going to have units of molarity, or that capital M, but they will match, right? Your concentration of A will match the rate concentration that you're looking for. Are there any units on order? There are no units on order. Right, it's just 0, 1, or 2. And then what about the rate constant K? Do those have set units? No, these have no set units. These will change depending on overall rate order. So as an example, if we have rate is equal to K times A, if we have a first order reaction, then you only have one molarity component of your concentration. So if we want rate to be in molarity over seconds, and we already have molarity, what does K need to be in order to get, what do you need to multiply molarity by in order to get molarity over seconds? 1 over seconds. Yep, so K is going to be 1 over seconds for a first order reaction.
You're like seconds to the negative.
That's perfect.
That-
Yep.
so like-
Nope, nope. It's really just your preference. Sometimes exponents get weird, so what if we had a second order reaction where A squared? Right, we know that molarity, or that rate, always has to be molarity over seconds. What is our unit for the concentration component now? You're close. Yep. So if we're talking about just A, and then we're squaring A, what have we done to units if that's a molarity? Should be molarity squared, right? We take a molarity times molarity, molarity squared. So how do we get from molarity squared to molarity over seconds? Right, think about this just as an algebra problem. If we're going to solve for x, what do we divide by? We divide by molarity squared. So we end up with 1 over molarity times seconds, or m negative 1 times s negative 1. Okay, so once you get above the second order, then your molarity starts becoming a part of your denominator, because you need to negate anything that you're being multiplied together in order to get to the units of K.
By rotating include the negative by one, by just saying it's n to the negative 1 times s to the negative 1, we know that it's, so that's a second order.
That's an overall second order reaction. Yep. And second order could look two different ways, right? You can have that second order. This is second order, right? Because you have 2 as your exponent in the first one. You have 1 and 1 as your A and B exponents. So overall, you have a second order overall rate order. Respectively, A and B are first order, but together you have a second order reaction. Does that make sense? Okay. One shortcut, or one thing that I like to remember for this, is that K will be equal to 1 over seconds times molarity to the overall order minus 1. So if you take your overall order of 2, you subtract 1 of it, then you have molarity to the first power, right? But just in the denominator. And so you're left with seconds times molarity, or molarity times seconds, which matches what we just found in the example above, right? So if we had overall third order, then our units of K is now 1 over seconds times molarity to the 3 minus 1. So that's 1 over seconds times molarity squared. Okay, so that's just a little shortcut if you're looking for an easier way, or just an easy way to recognize something. And then the most important thing to note from this is that your coefficients does not equal rate order. So if you have 2A plus B goes to C, right? Then your rate law does not equal A squared times B, right? That doesn't happen. You can't conclude that. It might be rate is equal to K times B to the third, right? You never know. You have to have more information than just the overall balanced equation in order to come up with the rate law. So, right, you can't switch back and forth between the two. You need to be given more information. Questions on that? Okay, so then we can talk about the method of initial rates. So this involves experimental data. Right. So as an example, we have this here, and you would be given a couple experiments. And you'd be given initial concentrations of your reactants, and then you'd be given initial rates. Okay, so this will always come from experimental data in order to determine the rate law for this reaction. So when you're doing this, you would always be given a table. So if you see a table, this should where your mind should jump to. And when you're looking at these, you want to look for trials in which the concentration of A or B, depending on what you're trying to find, is changing while the other reactant is staying the same. In those cases, that means that the only change that's happening in the rate is because of the change of that reactant. So when we look at, for example, going from trial 1 to trial 2, we jump from 0.1 to 0.3 in both A and B. So when we look at the initial rate, we see that that changes as well. But we don't know how that rate is changing because both of our concentrations are changing at the same time. So it could be contributing from one, the other, or both. Right, so this is probably a bad one to look at. But if we look at, let's say, 1 and 3, we see that if we hold A at the same concentration, right, we don't change the concentration of A, but what do we do to B? We triple it, right? So this goes times 3. What happens to the initial rate as we go from 1 to 3? Nothing, right? So this says times 1. So if our concentration is changing and our initial rate is not changing, what order does B have to be then? 0, right? When we have a 0th order reaction, I appreciate your enthusiasm. When we have a 0 order reaction, that means that the rate of the reaction is not dependent on the concentration of that reactant. You could have one singular molecule, or you could have a whole mole of molecules, right, which is 6.02 times 10 to 23, and it would go at the same rate, right? It doesn't matter if you have one or a ton, it'll go as fast as it wants.
The more it changes by, that's like higher up on the order list.
Yes. Yep. Right. So we'll see that when we do more examples, right? But if it's not changing, if that rate doesn't change, then it's always a 0th order. Okay, so we know that B is going to be 0 order. So in this example, there is no case where, oh yeah, there is. Okay. So when we look at A, we're looking for 2 trials in which B is staying the same, but A is changing. Does anyone see a trial? From 2 to 3, right? So, and you can either look at it going from 2 to 3, or you can look at it from going from 3 to 2, whatever is easier for you to see. If you go from 3 to 2, I see that we go from 0.1 to 0.3, and in my mind, I like to say it's multiplied by 3 better than it's multiplied by 1/3. So, right, we're changing by times 3 as we go from 3 to 2. What happens when we go from 3 to 2 in our rate? You also multiply it by times 3. So if we go times 3 and times 3, they're changing at the same magnitude. If they're changing at the same magnitude, what order does that correspond to? That would be 1, right? And if we think about that, right, rate is equal to K times A to the first power. If we times 2 our concentration of A, we multiply it by 1, right? We're not changing that times 2. Our rate would also have to be times 2. K is a rate constant. It doesn't matter the concentration that you're working with. For that reaction, it will always be constant. It will always be that same number. So in order to keep those constant, when A multiplies by 2, the rate also has to multiply by 2. Yes.
So I don't get why it's 0 for the B. Like, because what I did, like, for the A was I put like 3 divided by 3 because the rate and the it's 71. So why is B 0?
Great. So if we look at it in terms of the rate law, we have rate for reaction 1 is, or let's do rate for reaction 3 is equal to K times B, and we don't know what this is, so we'll call it X as our exponent for the order, right? So, and then we can say that if we divide these, the rate of 1 times K to the B to the X power, because between trials that our order is not changing. The only things that changing is the rate and the concentration. So if we look at it this way, we can plug in all those values from the table above. So rate 3 is 3.0 times 10 to the negative 4. We don't know K, so we're going to keep it as K. Our concentration for B is 0.3. And that's to the X power because we don't know what it is. And then for experiment 1, our rate is also 3. We still have K, and we have 0.1 to the X power. When you divide these two rate laws, what is 3 over 3? That's 1, right? So this is 1. What can you do to the K's? Those can cancel out. Since 0.3 and 0.1 are raised to the same exponent, you can combine them. So that's 0.3 divided by 0.1 to the X power. So what is 0.3 divided by 0.1? 3. Yep. So that's 3 to the X power. So now you have to say what exponent in that X spot gets 3 equal to 1? 0, right? Anything to the 0th power is 1. So 1 equals 3 to the 0, which turns into 1 is equal to 1. Okay, and you could do that for A as well, right? If we look at going from 3 to 1, we have, or what is that, 3 to 2? We have 9. We're going to divide that by 3. Right, so in this case, this is now 3 is equal to 3 to the X. So what does X have to be in order to make 3 equal to 3? Should be 1, so X is equal to 1. So that's why for A, that becomes first power. And then for B, it's 0 power.
So like, I guess, like, whenever you did it without the work, like, is there a way to do it without writing everything out?
Yep. And that's where we were comparing how it's changing in magnitude. So when we looked at the purple arrows, right? So if we looked at this one here and this one here, when we changed 0.1 in B to 0.3, we said that was a times 3. When we looked at the rates, we said that's a times 1. So if the rate is not changing, the concentration is changing, it's always 0. Okay? If you're now 3 to 2 for A, we said we went from 0.1 to 0.3, that's times 3. Your rate changed in the same magnitude. So that would be a 1 first order. Yep.
Like, let's say from 0.1 to 0.3 to this times 3 change the A and then the rate, even if the B was if it changed to like 0.1 to 0.2, would that really even matter?
Nope. Correct, right? So, right, it wouldn't matter. So if we look at, right, when we look at trial 2, if we go from 1 to 2, we're tripling our concentrations in both A and B. But what does our rate do? It only triples because the only thing it cares about is that A tripled, right? So they have that 1-to-1 magnitude change. And so it'll be times 3 and times 3. So we don't really care about B at all. Okay. So, and then if you want to look at it for second order, because that's the only one we haven't done yet. If you see like, if you see 0.2 to 0.4, and then it's 2 to 4, 2 to 8, right? This multiplies by times 2. This multiplies by times 4. right? So if we're squaring the difference between magnitudes, then it's a second order reaction. That just takes practice. Yeah. No, thank you. Have a nice day off.
So if we go with like the two to 4 50
Mhm.
and then we would also have like, could there be like a change in B that's also 2 to 4? How would that change
The rate.
the rates?
Yep. So if we had something where, right, this was 0.1, right, this is A, and this is B. Right, we had 0.1, 0.2, this was 0.1, 0.1, 0.1, 0.2. I'm just gonna come up with numbers. Right. So if we're looking at it this way, we have in our first two trials, we have B staying the same and A changing. What happens is we go from 0.1 to 0.2. What is the change in there? That's times 2. What about 5 to 10? Times 2, right? So what is the order for A? The order is, it's first order because our times 2 and our times 2 are the same, right? If it was 0.3 and 15, right, it would be times 3 and times 3. As long as those multiplications are the same, it's a first order, okay? So we know that A has to be first order, okay? What about as we go from, let's say, 1 to 3? Right now, in this case, from 0.1 to 0.2 in B, what are we doing? Multiplied by 2, right? So what does that mean for the order of B? It's also first order, okay? So if we look at rate law, we say that rate is equal to K times A times B. So if we have 2 times the concentration, what does it mean our rate is multiplied by? 4, right? Because it's all raised to the 1 power, so 2 times 2 is 4, so that means that our rate has to be 4 times the rate. Okay, now let's look at, let me erase some of this. Right, now let's look at going from this guy to this guy. What did we do in A? We multiplied by 2. What did we do in B? We doubled it. What did we do to our rate? Multiplied by 4. What did we expect to happen? Multiplied by 4, right? So it still changes in the same magnitude, right? They're independent of each other. Whatever A does, it'll affect the rate in the way that it's supposed to. Whatever B does, it'll affect the rate that it's supposed to.
So going from A from 0.1 to 0.2, and then B from 0.1 to 0.1, at least in the first two rows, that A and B are both still first order, even though that the B isn't directly changing the rate.
Correct, right? Because the rate is dependent on the concentration of B. So at that initial 0.1 and 0.1, we have a rate of 5. So that's like your baseline, right? So if we're keeping B the same and we're multiplying A by 2, then any change that happens in the rate is because the concentration of A changed. Okay? Same thing for 1 and 3. Now A is staying the same, so now anything that happens in the rate is because B changed. Okay? For 1 to 4, both of them changed now. So now the rate is changing because A changed and B changed.
Yeah.
Okay, does that help a little bit?
Mm.
Okay. The more you practice with this, I think you have some homeworks on it. The easier you'll see the changes happening, and I think it helps it a lot too. In worst case scenario, if you draw it out or write it out like we did up here, like in these situations, and you just divide by the trials, it should work itself out.
Yep.
Okay. Any other questions on?
Looking at the slopes, like the natural log. I was a bit confused on.
Yeah, perfect. So when we look at your graphs, right? All of these are going to be time on your x-axis. Your y-axis is what is changing. So you'll have your concentration of A, you have the natural log of A, and you'll have 1 over the concentration of A. The concentration of A, think of this as like if we were to graph 0.1, 0.2 over time, right? So you're looking at how does the change of this A look like on a graph? If it is, in order to determine the order, it will depend on which one of these 3 graphs gives a straight line plot. Okay, so we could see an exponential decrease for A versus time. Is that a straight line? No, right? So it's not going to be what is just A over time. What is the order for that one?
For the first one?
Yep. Yep. So this will always be a 0 order. If you see something that just has concentration over time, then it's always going to be the 0th order. Okay. If we have a log over the concentration, right, and that gives a straight line, what order is that one? That's first order. What do you think 1 over concentration is?
No positive slope.
It's a positive slope, and what order does that correspond to? Second order. Right, so that would look something like this, right, for this case. So which one of these produces a straight line? The first order one. So what is the order for A? First, right? It's a first order reaction because the straight line plot is the one that has the first order kinetics with it.
So anytime that there's just the change in A over time, it's always going to be a zero order.
Yep. So if I asked you, so what is the order for A in this scenario? Second order, right? Because why? That's when the straight line occurs. Okay, and then for these, right, they're always going to be, when they're in that graph form, they will always be y is equal to mx plus b. in this case, for 0 with order, M is going to be negative K. M will be negative K for first, and M is just K. So that's your rate constant. So you'll be given a negative slope. So K is the positive version of the slope. Okay. A rate constant will never be negative. So you never want to pick a negative rate constant.
So even in a situation like above, where we chose first order, the K is still positive?
The K is still positive because this would be, y is equal to negative 0.500 x
And
plus
the
b.
negative.
So then the K is equal to 0.0 is equal to 0.500.
Yeah.
Yeah. Okay. Yep. That they can give you like in lab, you can take an experiment and you can have your concentrations over time. You can plot it and then you can manipulate it, right? Take all of those, take the natural log of those concentrations, take the inverse of those concentrations. You can plot those concentrations and then figure out which one gives you the best straight line. You can figure out the order for the reaction for that particular experiment. Okay. Any other questions? I think that, I think that's where y'all ended today. Yeah, you'll talk about Half-Life on Monday and stuff. So, yeah. Do you feel better?
Yeah.
Okay.
Got it.
Yeah.
Since we-
Yeah, sometimes you need to just sit with it for a little bit or hear it explained a little bit different.
Thank you.
Yeah, alrighty. Have a great extra day off.